Last time we took a look at how to create just a simple class. Okay. So for example, we created a class called student, if you remember. We discussed the convention. What's the naming convention in C#? Okay, every language has its own naming convention. So we discussed that class names start with uppercase. Okay. If you're creating any private variable inside a class, that starts lowercase. Okay. All the public fields or public methods start with uppercase. Okay. And the default in C#, if you remember, was private, right? Okay, so for example, we created 5 fields, and our first field was, for example, string first name. Okay, unlike C++, where we use underscores to separate out multiple words, here we write it as a continuous thing, but each following word starts uppercase. Okay. So what's the default visibility as I create this? Private, right? Okay, so we expose each private field through tiny get and set functions, right? And we discussed that we can write it in the Java style, or we can use the C# property style. What's the property style? What does it look like? We say public string. Remember, all public fields by convention start uppercase, right? So that's why we will make it first name with a capital F. Then inside it, there will be a get part, return first name, and there will be a set part, first name equal to value. Okay. So then we also saw that rather than us typing all of this code ourselves, what was the shortcut to it? Once you type this black part over here, then using Visual Studio, you right-click on it, refactor, encapsulate field, and it will automatically type the blue part. So it makes our life a lot easier, right? So very similarly, we created, so this is one field, right? The private is first name, and the public property is first name with capital F, right? Okay, very similarly, how many fields did we create over here last time? Okay, we created a field called last name. We created a field called ID, test1, test2, right? So let's pretend every student has these 5 fields, right? Now, typically, once we create a class, remember we discussed classes like a template. Okay, nothing exists in the memory of the computer unless we create an object of it. So for example, if we are creating a university application where we have 6,000 students, we'll create 6,000 objects of it. Each one will have a separate first name, last name, ID, test1, test2, right? So one of the important things to understand is, as we run a program, what gets created in the memory if somebody, remember last time we wrote a small program to test this code, and our program was something like this. Okay, we created a button handler. Okay, meaning if you click on it, it will call that function. Okay. And in this button handler, we created one object of the student class. So our code looked something like this. Student S1 equal to new student. Then we did S1 dot first name equal to whatever S1 dot something, S1 dot, right? And then we called something like this. Message box dot show, and something grade equal to something plus S1 dot
compute grade.
Did we write the compute grade last time?
Yes.
Okay, we did. So let me add one more function over here that we wrote. we also wrote one function, public string compute grade, and it does some computations and returns, for example, A minus, B plus, or whatever the case may be, right? So our test code was something like this. This was the red part was our test code. Okay, so one of the important things for us to understand is, hey, why are we writing this new student? At first, for those of you new to this kind of programming, it may be confusing. What is student S1? What is this new student? Okay, what happens when we say S1 dot first name equal to Bill? What does the computer do, right? What happens once we say S1 dot compute grade? And I forgot, anytime we call a function, we have to have parentheses, okay? So to clarify these fundamental concepts, okay, so let's take a look at a computer. See, whatever program we write has to execute on a computer, right? What is a computer? A computer is a CPU connected to memory, and this is what we call RAM, for example, random access memory. So for example, when you go to buy a laptop, they sell you with 8 gigabyte of RAM or 16 gigabyte of RAM, right? So that's the memory, right? There's also a hard disk connected to our CPU. So for example, all of our files are stored over here, right? Now, first important concept you need to know is that if we wanted to run a program, it cannot run by sitting on the hard disk. It has to be loaded in the memory of the computer. Once it's loaded, then the CPU has all the circuitry to add, multiply, subtract, and so on, divide, take the cosine, take the square root. All that circuitry is inside the CPU. So once the program gets loaded, the CPU brings it, goes to the memory, brings the instruction, and executes it, right? Okay, so if we write, for example, a C# program like this, okay, if we, in the beginning, remember as we are typing it through Visual Studio or through whatever editor we are using, here's our C# program. Okay, so as I mentioned, it cannot run by sitting on the hard disk. Okay, so how do we run it then? Okay, if we load C# program into the memory of the computer somehow, okay, the problem is it will still not be able to execute because CPU does not understand C#. CPU does not understand C, C++, C#, Java. What language does the CPU understand? Machine language. Okay, so this will still not work. Okay, so what do we have to do? This is where we use a compiler. Compiler is a special program. So before we load it into the memory, we pass our program through what we call a compiler. Compiler's job is to convert whatever language we have into the machine code. Okay, so for example, on the Windows operating system, it will produce a file with an exe extension, right? Now if you double click on this exe file, then what the computer does what the operating system does it loads the exe file into the memory. So this is all machine code now. Okay, once it's loaded in the memory, now the CPU can bring one instruction, execute it, go to the second instruction, bring it, execute it, and can execute the whole program, right? Okay, the other thing to understand is, as we are running this program, it will need additional memory, okay? For example, let's forget C# for a second. Let's go to the plain old C language. So suppose in the C language, you wrote some kind of a main where you said something like int a equal to 5, int b equal to 7, int c equal to a plus b. Okay, let's take a look at this very, very simple program that you wrote in C language. Okay, Now, if we wanted to run it, can we simply load it into the memory of the computer? No, we have to first compile it, right? So once we compiled it, so there are 3 instructions over here. These 3 instructions will get converted into machine code, maybe 3 instructions, maybe 5 instructions, maybe 6 instructions. Machine code, one high-level language may get translated into 2 or 3 or more machine-level instructions. So anyway, whatever that translation was, okay? Once this program is converted into the machine code, now if we try to run it, take a look over here, what will happen as the CPU tries to execute it, okay? See, it has to declare some memory to store A, okay? So in this memory, we have 2 special areas. One is called the stack area, one is called the heap area. Okay, both of these are used to allocate memory as our program executes. Okay, so for example, anytime we call a function, including the main, if we declare some variables, the memory for those comes from the stack area. Okay, so all local variables, meaning variables that are declared inside a function, so variables declared inside a function, these are called local variables. Okay, the memory for these comes from the stack area. Okay, so all local variables are allocated on the stack, meaning the memory for those comes from the stack area. So as the computer is executing, it will take a look at int A, for example. So it will allocate some memory over here for variable A. Okay, then A equal to 5, it will store 5 over here. Then int B equal to 7, it will allocate memory for B. B equal to 7, allocate the memory. Int C, so it will allocate memory for C. C equal to A plus B, so it will go to wherever A was stored, wherever B was stored, so it will store 12 over here. Okay, so what happens to the stack area once the program ends? Do we need this memory? No. So the machine code that was generated over here will automatically clean up the stack, meaning this will go away as soon as the function where these were declared